All right, guys. So one thing that I really wanted to make sure of is that we're all on the same page with respect to the mathematical background that's needed in order to do uh, circuit analysis, right? One thing that is used over and over and over and over again in this type of study and this type of endeavor is complex number algebra. And so I want to spend some time reviewing some of the basics of complex numbers so that we're all on the same page and can keep on working with circuit analysis, in particular once we start getting into chapter 9 and the later chapters. So let's begin with complex numbers. And this is kind of an overview. And this is going to be an overview number 1. Complex numbers, the study of complex numbers is extremely, extremely rich, and I can't do it in just one short video. So there will be multiple smaller videos that will make this material a little bit more digestible. But let's begin with our definition. A complex number is a number of the form z is equal to x plus jy, where both x and y belong to the set of real numbers, and j is the complex unit, which is the square root of minus 1. Right? Now, I do want to make a very quick warning. I know that, again, this is a review. In electrical engineering, we tend to avoid using lowercase I as the complex unit. Right? So notice that we're actually using the letter J, not I. So note that I is not used as the imaginary unit. So if you studied this in high school or in some other class, chances are you use I rather than J. We have a very, very good reason for this. I has already been reserved to stand for current. We do not want to confuse current with the complex number unit. Now, complex numbers themselves can be represented graphically. So let's talk about the graphical representation. They're represented on a plane, right? So two-dimensional graph. The vertical axis is the imaginary plane, and so it is the imaginary part, Im, of the complex number, which is the value y. So this is the imaginary part. Of the complex number, while along the horizontal axis, we have the real part of the complex number, which gives us the value of x, like this. And notice that all complex numbers lie somewhere in those 4 quadrants. So for example, suppose that I had a complex number that lies, let's say, right here, so that say this is z is equal to x plus jy. If I go down over here, this is my x value, or my real part of the complex number. If I move over here, this is my imaginary part, or the y component of my complex number. And again, since x and y are allowed to range all the way from minus infinity to infinity, every complex number that exists can be found somewhere on this plane. Now, one critical observation is, I'm sure that you guys have also seen polar coordinates. This form for a complex number is what we call the Cartesian form of the complex number. There is also what they call the polar form. Now, this complex number itself can also be located on the plane by stating from the origin what is the distance out to the complex number in question. That's the distance r. And if you go from the positive x-axis and turn counterclockwise until you actually hit that line where the complex number happens to be located, this is the angle theta that's used. Now, we can use some basic trigonometry in order to go back and forth between the Cartesian coordinates as well as the polar coordinates. So we should be able to see quite clearly that since this right here is the adjacent side to that angle, this is going to be r times the cosine of theta, and that's the value of x. Since this and this are identical, we can also say that this side, y, is r times the sine of this angle. Right? So here, the relationship between the Cartesian form and this polar form for the complex number is the following. So here you can say that x is equal to r times the cosine of theta, y is equal to r times the sine of theta. So if you happen to have the polar components, r and theta, you can crank them through these equations and you'll get the Cartesian values, right? These can also be inverted. And you can say that r is equal to the two Cartesian coordinates, x squared plus y squared square root. You can get that through the Pythagorean theorem. And also, the tangent of this angle is equal to y over x. I do want to give you a warning when it comes to this. You do actually have to be very careful with this angle because the angle itself can range all the way from 0 degrees all the way to 360 degrees. And when you're actually using the tangent function will not distinguish between components that are in the first quadrant, in the third quadrant, or the second quadrant and the fourth quadrant. So using that last equation, you need to be able to take a look at the geometry as to where that Cartesian number happens to be, that complex number happens to be, so that you can figure out the angle. Right? This also implies that, again, in Cartesian form, any number, the complex number has two representations. The first is the Cartesian form, in which z is equal to x plus jy, and we also have the polar form, in which z is equal to r cosine of theta plus jr sine of theta. Now, one thing that we're actually going to introduce in just a little while is Euler's identity. If this was the end of the story, and these were just the two different forms, then phasors, which we're going to introduce later on, would not be all that useful. But Euler's identity is going to allow us to greatly simplify mathematically the polar form and make it much more useful and suitable for easier calculations. But you should get at least a little bit of practice in working with some of these complex numbers, going back and forth between the Cartesian form and the polar form, because it's going to be important to be able to do later on.